Okay, in this video I'd like to talk about periodic trends and atomic properties. The question is, how do atomic radii and ionization energies vary based on the location of the element in the periodic table? What I expect you to be able to do is to state the trends, so in other words, tell me how they change, and explain the trends in terms of atomic structure, and use the trends to rank a given series of elements in terms of increasing or decreasing atomic radius or ionization energies. So let's begin with atomic radii. The atomic radius is an approximate measure of the size of the atom. So we're going to use this to compare the relative sizes of atoms of different elements. How do you measure that? There are a variety of different ways, but probably the most common is assuming that the element forms a diatomic molecule, that is, it forms a molecule in which two of the atoms are bonded to each other. It is possible to measure the distance between the two nuclei, and the radius then is that distance divided by 2. So I'll show you a chart that you may have seen in the first year of chemistry that is a section of the periodic table with spheres to represent the relative atomic radii. And let's look at the trends. By the way, this is an outdated numbering system for the groups in the periodic table. We don't use these anymore. We're essentially looking at groups 1, 2, and 13 through 18. So in the first period, and these values are in picometers, by the way. A picometer is 10 to the negative 12th meter. Hydrogen 37, helium 32. In the second period, we see lithium 152, beryllium 113, boron 88, carbon 77, and so forth. In the third period, we see sodium through argon. In the fourth period, potassium through krypton. In the fifth period, rubidium through strontium. And in the sixth period, cesium through radon. So let's summarize the trends. The period trend is that the atomic radii decrease when you move from left to right in the period. That is, the atoms get smaller. The group trend is that atomic radii increase as you go down a group from top to the bottom. That is, the atoms get larger. Why do they vary in this way? Well, as you move from left to right in a period, you might think that because you're adding more electrons to the valence shell that the atomic radius would get larger. But those added valence electrons are going into the same valence orbitals. But what else is changing is that the atomic charge, the atomic number is increasing, and therefore the positive charge in the nucleus is increasing. So we explain the period trend by saying that as you move from left to right in the period, the nuclear charge increases as you add more protons, the valence electrons are attracted more strongly, causing the orbitals to contract and the atomic radii to decrease. Why would atomic radii get larger as you move from the top to the bottom? We explain the group trend by saying that as you move down, the valence electrons are in orbitals that are in higher principal energy levels, which are larger, making the atomic radii increase. So the general trends are atoms get smaller as you move from left to right, they get larger as you move from the top to the bottom on the periodic table. Ionization energy, as its name implies, ionization energy is the energy required to take 1 mole of atoms of an element in the gas phase and completely remove 1 electron. This is sometimes called the first ionization energy because we're dealing with removing the first electron. And we form a plus in the gas phase plus 1 electron. These are all endothermic quantities because you have to put energy in order to remove an electron from an atom in the gas phase, and they are normally tabulated in kilojoules per mole. So let's look at some ionization energy values, and again, you don't need to know these, but we're just looking at the trends. Hydrogen 1311, helium 2377 kilojoules per mole. From lithium to neon, 520, 899, 800, 1086, 1402, 1314, 1681, 2088. From sodium to argon, 495 to 1527. From potassium to krypton, 419 to 1356. From rubidium to xenon, 409 to 1176. So what are the general trends? The period trend is that the ionization energy generally increases as we move from left to right. Okay, you notice that there are some slight blips in there. It wasn't a steady increase. There were some irregularities, but the general trend is that the ionization energy gets bigger as you move from left to right, meaning that you have to put more energy into the atom to remove the electron, meaning that the atom is holding onto the electron increasingly strongly. The group trend, on the other hand, is that the ionization energy decreases as you move from top to bottom. It gets generally easier to remove the electron because it's being held less tightly. So, how do we explain these trends? Well, as you probably noticed, the period and group trends for ionization energy are actually the inverse of the period and group trends for atomic radius. And in fact, we can use the same arguments to explain the trends in ionization energies. So as you move across a period from left to right, the nuclear charge is increasing, the valence electron is attracted more strongly, more energy is required to remove the electron, so the ionization energy increases. Pretty much the same reason why the atomic radius gets smaller. The group trend, again, as you move down the group from top to bottom, the valence electrons are in orbitals that are at higher principal energy levels and are shielded from the nuclear charge by an increasing number of core electrons. The concept of shielding is very, very important. Okay, so those core electrons basically partially neutralize the positive charge of the nucleus so that the outermost electron is less strongly attracted to the nucleus. Therefore, less energy is needed to remove the electron, making the ionization energies decrease. So we can use these trends to arrange the following groups of atoms in order of increasing atomic radius. Increasing means from smaller to bigger. If we look at rubidium, sodium, and beryllium, we see that rubidium is below sodium, so it should have a larger atomic radius. Sodium is to the left and below beryllium, so it should have a larger atomic radius than beryllium. So in order of increasing size, beryllium is smaller than sodium, is smaller than rubidium. Strontium, selenium, and neon, we see that strontium is below and to the left of selenium on the periodic table, so it should be larger. Selenium, sorry about that. Selenium is below and to the left of neon, so that means neon should be the smallest, followed by selenium, followed by strontium. Iron, phosphorus, and oxygen. Iron is to the left and below phosphorus, so it should be larger. Phosphorus is to the left and below oxygen, so it should be larger. So it goes oxygen, phosphorus, iron. If I arrange these in order of increasing first ionization energy, well, it'll simply be the reverse. But there is one more property I want to talk about that's mentioned in the textbook, and that property is electron affinity. Electron affinity is the energy change associated with the addition of one electron to an atom in the gas phase. So it's kind of the opposite of ionization energy. Instead of the energy you have to put in to remove an electron, it's the energy change that occurs when you add an electron to the atom in the gas phase. Okay? Now, I'm going to show you a chart that shows how electron affinity varies with atomic number, and it looks like that. So here are atomic numbers from 1 up to about 80 something. Here's the electron affinity on the y-axis. And as you can see, the electron affinity can either be positive or negative, meaning adding an electron is exothermic for most elements, but there are some elements for which it is endothermic. If you look at this graph for a while, it will become apparent to you that there really aren't any periodic trends in electron affinity. Kind of annoys me that they put it in the curriculum, but I have to talk about it. There are some generalities we can take from this, though. If you look at the elements that are down that have positive electron affinities, there are a few. Most have negative electron affinities, and this is pretty much all we can summarize. Electronegative nonmetals tend to have negative electron affinities, meaning that adding an electron is exothermic. Electropositive metals tend to have positive electron affinities, meaning that the addition of the electron is endothermic, whereas halogens have the most negative electron affinities. That kind of makes sense. We know electronegative nonmetals want to accept electrons. We know that electropositive metals really don't want to accept electrons. And we know that halogens, being the most electronegative elements, are probably the ones that are going to want to accept electrons most. Therefore, they have the most exothermic electron affinities. And that's pretty much it for periodic trends.